labs and as entrepreneurs. Yeah, so this is a very brief kind of introduction to about Professor Amit Sheth. But as I shared with you that his profiles like Google Scholar and also you may further have a look at it to know about him and his research more. With that, I would like to now request Professor Amit Sheth to please, sir. Please, it's the floor is yours. Please, over to you, sir. Please continue. Thank
All
you, sir.
right, thank you very much, Vishwanath. So I have an hour. I think there's plenty of time. Feel free to ask questions because I have kept my presentation to slightly under 60 minutes. Let me start with presenting, and let us hope you are able to see where I am. All right. Tell me if you are able to see where we are. My
Yeah,
landing page is
it's
probably coming
loading.
up.
Yeah,
Mm.
it has come.
All right. So as far as I know, your workshop is centered around semantic web.
Yeah, right,
Um,
sir.
and that means you have, gone through RDF, OWL, possibly some reasoning,
Yes.
and
Swirl and swirl, and then we also had the shackle. I mean, of course, that's not a reasoning purpose, but for reasoning, we use semantic web rule language. We had a tutorial also on that, and then of course the Sparkle language also we had, and then yesterday we had again the shackle that is for validation purposes of the data. So and SQWRL also we had.
right. So uh, I go back with semantic web quite even before the term semantic web was coined in 1993. I had a paper with my student, my first PhD student at that time. Actually, the paper came out in 1994. Um, that was in CIKM conference, and at that in that conference, the paper was titled "Semantic Information Brokering," and the idea was that you have multiple databases, and you have how would you and you have multiple ontologies, and how do you provide users to access multiple databases through the use of ontologies. In fact, the paper even also had the term of federated ontologies. The data sources we talked about were the traditional database sources like databases, but we also said it can be a web page. Now, if you think about it, you have ability to search or query through the use of an ontology on a web page. That is nothing but semantic web idea, right? But the term semantic web itself, so we use the word semantic information brokering. There's other term that has also been popular in the past called mediator. Um, but the term semantic web actually first appeared in 1999 in the book that Tim Berners-Lee wrote. In year 2000, in the very first uh, event, international event, it was a workshop on semantic web, very first one. Because remember, the term was barely coined, and not many people had seen it. And you may remember that the real, semantic web became very popular after the May 2001 article by Tim Berners-Lee, Handler, and Lassila. So in 2000, though, before that, uh, there was the first event on semantic web, and I was the first keynote speaker in that. The reason was that I had already a commercial company, and we had already built a semantic search technology that used ontology or knowledge graph to index or to kind of annotate automatically all kinds of content, XML content, web pages, HTML content, news and other things, and allow the search, directory, and many other things. I think I have a snapshot of the patent that was filed in year 2000, before, well before the semantic web paper by Berners-Lee and all. Anyway, so I did have first commercial semantic web company that was founded in 1999. Um, it was, I tried to convince Yahoo and Alta Vista and others to use that technology, but I was way ahead of the game. Sometimes being too early in the commercial context is a problem. Doesn't it's hard for customers to really think that. Still, the machine learning and all that were sounded very um, exciting, and people are looking for a lot more automation. If you go back those days, the reason the search was becoming very popular was that before the search for web search, it was not possible. It was not easy for Yahoo to keep up with its directory system. It had employed 9,000 people to essentially organize all of the web content, all web pages in a directory system. But number of web pages that now were created every day were in millions, and how can humans keep up with that? And hence search became very important, the one that can crawl all around the web and then index it and then do the search. But the initial search was obviously not semantic, and unfortunately I had a commercial product in year 2000, semantic search product, so it was too early. So they're still looking for, people still had to accept the regular search. And anyway, the company that I founded, the technology and all that still survives in some form, and people that I hired still are employed. But the company, after the internet market bust in year 2000, become focused on vertical market of financial services. Anyway, now because you guys all talked about semantic web, I want to share with you important you know understanding of the lay of the land, that in those early days when we started working on semantic web, in late 90s but early 2000s, basically around the change of the century, actually, there were two parallel two kind of groups or communities in the semantic web. There's one community that focused on logic-based formalism. It so happened that there was a group in Europe called, and they call OIL, and there is a group in US called DAML that created DAML language, DARPA Agent Markup Language. Tim Berners-Lee was a DARPA program manager then. And these, the inventors of those came from logic background, and especially then they settled on description logic. So OWL is based on description logic. Now, one group of semantic web researchers focused on use of OWL, consistency of knowledge representation, and reasoning. Unfortunately, that group never scaled too much. So when, let's say, large search companies, so when you're talking about Microsoft, Google, Facebook, well, Facebook had not come that time. Facebook came way later. In 2005 they started. But these large internet companies that had already started then, they found that this description logic based thing did not scale. There are, now I had first used RDF in 1999 on something called MREF, metadata reference link. You guys all know about href, right? In HTML. But how can you associate metadata on href, physical link, to make it more meaningful. So I'd use RDF for that. But when I started my own company, I chose not to use RDF. Instead, I used something very similar to property graphs. So there's something, and then so the second group, second semantic web community, were more focused on data and scaling. So they started settling on less expressive knowledge representations compared to OWL, but lot more scalable. Today, semantic web kind of survives, but really it is the second community that has won. The original community, the community that focused on OWL and all, survives, but it's a niche community, small community. The number of people that go to conference like that would be 100, 200, 500. But even recently, if you look at International Semantic Web Conference or ESWC, these are the two main conferences in semantic web. More and more of the conferences deals with linked data.
नीचे ना को दे दियो, नीचे जा रहा है ना, बेसमेंट में बैठी होगी.
And more of them focus on linked data and RDF and property graph as opposed to OWL. Anyway, now today I'm going to talk about this integration that is happening between a knowledge graph, which is very key, concept relevant to semantic web, and deep learning. And what has all of you guys should know that while semantic web was popular somewhat, machine learning was a lot more popular. So in the first decade of this century was all about machine learning and AI. And AI is a much larger, kind of community compared to, let's say, semantic web. And starting 2012, deep learning became very popular. So for the last 8 years, it has all been deep learning. What is interesting here is that more and more people recognize that data alone is not enough, that you really need knowledge to build intelligent systems. And while there has been some massive, significant progress in deep learning, for example, GPT-2 and GPT-3 or in BERT and other language models as an example. As I will discuss, you will see that, for example, they do natural language processing, but they don't do natural language understanding. They can do things similar to what is in the text, but they cannot put together 2 + 2 = 4. Okay, so I'll share with you why there is some key learning from semantic web world, moving of the second community, of the type of second community, not the first community type, not the description logic guys, but the other ones who have been in the graph forms. Why that is moving, very much coming together. And then what is its implication? With the deep learning, basically it is well known that there is black box effect, that it is very hard to or impossible to explain how deep learning works. And how can we pry open the black box? With infusing the knowledge or semantics. That is what this talk is about. So we have now this knowledge infused learning that I'll be talking about. There are a lot of people now already working on that. Several of them are my students, postdocs, and some collaborators. For example, there's a company called Imbibe. This is a Reliance Geo funded company. that collaborates with us, and they use knowledge graph in a very large way, and also incorporate some of the things that I'll talk about today. So this is the current snapshot of the AI Institute that I founded in 2019. I moved with a part of my team from Wright State University, where I had knowledge-enabled computing, Center of Excellence for Knowledge-enabled Computing, and now it has grown significantly with projects to, uh, in collaboration with majority of the colleges in our university. Ours is a large university, and it's a tier 1 institution, state flagship university. So a lot of expertise in the university. In the center of this all, you see some of the areas in AI that we work in: knowledge graph development, knowledge deep learning, knowledge infused learning. So this is what I'll talk about. But and interpretation, explainability, trust and ethics, that kind of thing also we talk about. But there is a lot of other things that we work on that I won't talk about today. Okay, let me see. There is a pointer. There's a pointer. Okay. The other thing we do is translational research. So meaning research that is applied to real world. As Biswanath was saying, I have founded 3 and co-founded 4 companies, and this is because we often apply technology to a lot of different areas. You can see here: medicine, healthcare, nursing, disaster management, manufacturing, public health, social good, education, and others. Okay, so today I'll talk about knowledge graphs, knowledge graph meeting deep learning and hence knowledge infused learning, and then explainability and interpretability with some examples from healthcare, and if there is time, some more examples. And I'll be happy if you want to ask any questions as I go along. So knowledge graph is a structured knowledge in a graph representation, in many cases labeled property graph or RDF or its variants. We cannot escape the class expressivity and computability, the expressivity and computability trade-off. So what I mean to say here is that if you choose a more rich model, for example, going from RDF or property graph to OWL, where you can represent the constraints and other things, then there is higher investment upfront. There is higher maintenance and management thing. There is more challenge in being able to create and maintain those ontologies. Thus, it takes longer time to create an application or a product, and hence this graph-based formalism of the type I'm talking about is taking front seat right now. Now, key differentiator in what we need to do, the minimum, in my view, the minimum level of expressiveness is to have relationships. There's a talk I had given in a long time ago in 2003, relationship at the heart of semantics and semantic web. So if you're interested, you may want to look up that work. What is the critical role of relationship in everything I do? I mean, ultimately, that matters. Entities and relationships matter a lot more than all the other forms of modeling. Now, there are many other forms in which we incorporate knowledge, ontologies, knowledge bases or flattened graphs, lexicons, and such. This is the patent that we had filed, and it was awarded in 2001, around the same time that that paper came out in Scientific American. And you can see the title. So this was the first patent on semantic web, and it is also in its title. So it is semantics and methods for creating a semantic web and its applications in browsing, searching, profiling, personalization, advertisement. And there is a link here, the bit that takes you to an article, or you can go to my LinkedIn and go to my LinkedIn articles. The first article is about 15 years of development since our first patent, from around the time of this patent to around the just after Google came up with semantic search in 2013 and knowledge graph. All kinds of how what has happened in that time period in semantic area, semantic search area. You can see on the right hand side a kind of a knowledge graph, or an ontology, or a world model, whatever you want to call it, that is which is domain specific. Now in the last few years, there is a huge growth in broad-based and domain-specific knowledge base. So on the left-hand side, you see a variety of broad-based knowledge graphs. DBpedia is probably the best known. Wikidata is coming out very strong, and you're going to have, or you already had, I don't know if you, I think you probably already had talk by Dan.
We had the talk
So,
yesterday.
okay. But there are, and there's others. So this Freebase, by the way, happened to be in a company. The name of the company was MetaWeb. Freebase happened to be the manually developed 5 million node um, knowledge graph that Google acquired, all manually developed. And then it has built a very massive billions of node knowledge graph now. The important thing to note is that Google's knowledge graph has not been all automatically developed. Google had actually a project called Knowledge Vault to do a lot of things automatically, but in reality, they have thousands of people working. It happened that I was giving a keynote in China, in Chengdu, China, in 2017, and there were and the whole conference was on just knowledge graphs, and there were 600 people in the audience. So to some extent, I can conclusively tell you that China understood the value of knowledge graph well before many parts of the world did. And hence, when I gave the keynote, there were 600 people just on the 3-day conference on just knowledge graphs. Well, I happened to meet a person working for Google's knowledge graph, and he did confirm that there are thousands of people working in maintaining the knowledge graph. A lot of work is still manual. On the right hand side, you see a bunch of healthcare specific knowledge graphs, and for many other domains, there are again other knowledge graphs. So what it says is that now the one interesting thing is that when you want to develop such knowledge graphs, at least the public knowledge graph, majority are community developed, developed by a bunch of researchers. Of course, there are also so-called enterprise knowledge graphs, which are proprietary, which are owned by the company. So this was a paper, I think, a couple of years ago or less than 2 years ago. And, it was authored by people from Google, Amazon, Microsoft, and eBay and IBM. And they all talked about their knowledge graphs, and they are telling you what kind of things they have in their knowledge graph. So it says Well, they have types of entities and relationship attributes in the graph, and most of them have things like products, things like people, things like organizations, things like location. These kind of standard activities that are broadly used in general purpose applications like search or merchant e-commerce. And you can see the size and so on and so forth. The companies that also develop contract manufacture, uh, on contract basis knowledge graphs. On the bottom, you can see Mana. It was one such company. Now, these are some of the knowledge graphs that my group or that I've been associated with. In the left, you see empathy ontology, which is an ontology for the uh, emergency domain, disaster domain. On the right, you see an ontology by a company called EZDI. You can go to ezdi.com, which I co-founded, and we wanted to have ontology enhanced natural language processing of clinical documents, and that's what the company is about. So we developed an EZDI knowledge graph. There's a patent also that discusses this thing in more detail. And then there's even, this is a very large knowledge graph. There's a large knowledge graph that this Imbibe company that, as I mentioned, has developed. This is all about education, all kinds of central board exams in India, or biology, 10th, 11th, 12th grade biology, all these kind of subjects related knowledge is what this knowledge graph has. Now, one interesting thing here is that the concept of knowledge graph is not only limited to domain, or we largely talk about this domain specific knowledge graph, but there are knowledge graphs of all variety. For example, you may have knowledge graph about value that society has. So as AI system more and more interact with humans in the field of this chatbot or virtual agents or conversational AI systems, when these systems interact with humans, you have to understand humans more. So in our for example, humans have the norms, societal norms. Humans have law. Humans have, so you do a interaction between people in a legal framework, or an electron or a autonomous vehicle running on on roads with people around, which is a society, has to be abided by norms and law. And hence, as these AI systems are embedded more and more in society, there are many other kinds of knowledges that need to be captured. And so there's this paper that discusses knowledge graphs to empower humanity inspired AI systems. Now, the one what has been evolving these days, and one of the very hot term is neurosymbolic AI, or computing, or computing that combines statistical AI with symbolic AI. Now, what you guys have done throughout this workshop is largely a part of symbolic AI world. And the other world, which is much larger and also highly successful, that uses deep learning techniques, is the neural network, is a form of statistical AI, is part of statistical AI. and it is you know it has shown amazing success for several well-defined tasks, and I'm going to talk to you about its limitations and failures also to some extent. But um, uh, uh, I teach a class called Semantic, Cognitive, and Perceptual Computing, and that uh, what is recognized is that um, there are different forms of um, computations that are necessary in an intelligent system, and there is, we can learn a lot from other areas, other fields. For example, from the cognitive science, there is this concept of top brain and bottom brain. A behavioral economics Nobel Prize winning behavioral economist, his name is Daniel Kahneman, wrote the book about System 1 and System 2. And the System 1 is one that kind of supports perception. It is a very fast understanding of the data, but with a lot of errors. So for our vision system, for example, human vision employs System 1. But then somehow we even whatever we watch, whatever we listen, all of them, then we think deliberately, we plan, we explain. All of that belongs to System 2. System 1 is fast thinking with a lot of errors. System 2 is slow thinking with a lot more precision. Okay, hence they need to come together. So my group and a lot of other people are these days very busy developing hybrid AI techniques that combine these two things you see on the the System 1 perception statistical AI and the System 2 cognition and symbolic AI. But the point I want to make is that as we develop the system, at least in our framework, knowledge graphs or knowledge and experience play central role. Some people like Hinton are trying to build a system without knowledge. Others, are trying to build system with using knowledge. I'm in the camp where we try to use explicit knowledge. There is also, by the way, in this one here, there is also implicit knowledge. In this one here, there is explicit knowledge. So why knowledge graph? And let me just take the example of part of AI that belongs to natural language processing and natural language understanding. So here you will look at some of the points, and today in my lecture I will only talk about use of knowledge graph to better contextualize the words, and also address the question how much context is needed to provide more precise answer. So okay, let's look at this example. So pay attention to this text here at the top, a paragraph in the news article. Let me demonstrate to you what it takes to try and understand what this news article is. And I will also try to convey to you that no amount of sophisticated deep learning can help you understand what this language says without the use of knowledge. So if I were to then use DBpedia and do semantic annotations, I'll be able to use categories, subcategories, their properties in DBpedia. and I will be able to understand several terms here. For example, CDC is a concept in DBpedia. To the extent that you can understand, CDC is the acronym for Center for Disease Control. Influenza is concept in DBpedia, but it is described in a different way, at a different level of granularity, and not necessarily in the way that is meant for a clinical expert as compared to SNOMED CT, for example. So both may describe influenza, but they describe influenza in different contexts with different level of granularity and details. Now, using that DBpedia, you may be able to understand CDC, influenza-like illness, influenza season, and high proportion, those kind of concepts. If you use neural parsing with self-attention, you might be able to understand these other items that are in color. If you apply on the right hand side SNOMED CT and its hierarchy of entities, you will get more tests for coronavirus or influenza of one type. These are the things that will become understandable. How it will become understandable? Well, you'll be able to annotate it, right? In semantic web, one of the key things is that you're given a text, let's say web page or news item, that using the ontology, you are able to do soft matching and say that this particular phrase or words is described in my ontology using this node, this concept, right? And this is how you endow the meaning. Once you describe using a particular concept, you may be able to find a lot of things around it. For example, influenza is a concept in the ontology, and then you can see other kinds of virus-based, vector-based diseases, and you can sort of bring to bear that knowledge and understand the content. Going through this process, now you can identify relevant entities like individuals presenting is adding influenza season, men are showing influenza-like illness, high proportion, all these kind of different concepts and entities then that can be searched for. What I'm trying to say is that you have to in the processing I've shown, I could be using a variety of things on the here. Snowstorm, that gives you SNOMED CT, Berkeley neural parser, and GDELT. These are all the kind of things that may be used to understand these stuff here. Sorry. One thing that is interesting is, though, as you think more, there are different types of knowledge that will come into picture. If you want to understand text like this, it's not that easy. You can start with statistical AI and you can get something like that, but you see, this is not all that exciting. It is the use of DBpedia SNOMED that makes things more interesting. But that's not all. You can start with first linguistic knowledge, such as in WordNet, common sense knowledge, such as in ConceptNet, then general broad-based knowledge, that is like in DBpedia, then domain-specific knowledge. For example, it may be drug, protein, and here it is SNOMED CT, to really make this information meaningful, to be able to understand, to make the computers understand what the text says. Now, if you were not to use all of this knowledge, Then with deep learning, you face a lot of questions and a lot of problems. And then these are all, discussed here. And in one of our paper, there is a paper by the title of this talk, Semantics in a Black Box, that discusses several of these things. Where, without external knowledge, understanding symbolic knowledge, taking care of bias, personalizing or using abstraction, those are all the things that are not possible or nearly not possible. There are also other issues that are very important that knowledge graph make it easier to solve. For example, these large knowledge graphs like DBpedia or Snowmed City have a lot of that knowledge. When it is combined with deep learning, can reduce our need to have labeling done. As you know, many of the deep learning techniques, all the semi-supervised and supervised techniques require huge amount of label data. And one way to kind of reduce that need for label data is to use knowledge graph. If you do deep learning using state-of-the-art deep learning, you can come up with all of these clusters. But how would you name the cluster and what they mean? To be able to do that, you will need the knowledge graph. So that there's buprenorphine here. These are all the items along buprenorphine. On the right hand side, I show more, empowering more. So here you can see there are nodes connected by edges, but the edges are they are not full relationship. They are just statistical relationships. But I can start applying knowledge graph that have not only entity but label relationships. And in that case, all this processing become a lot more enhanced, because now you have relationships added to the to the nodes. So among there is a acute and kind of recognition that deep learning systems suffer with a lot of biases. So example one is a historical bias, that historically majority of the CEOs of Fortune 500 companies have been men, in fact white men, and among them almost all are white men. Currently only one Fortune 500 CEO is an African American, and only 5% are women. So the deep learning algorithm will understand that CEO is a man, right? But unfortunately, it's a bias the society prefers not to have. There may be a representational bias. Only 1 and 2.1% images come from China and India in ImageNet. So it will not be able to understand how people look in the scenes in India and China. It will have a very significant bias towards the West. Similarly, there will be measurement bias. Over the period of time, when you collected crime data, and you see very many African Americans, you will think that crimes are committed by African Americans. That would not be also good, and so on and so forth. So one way to handle this bias is again to use knowledge graph. So now I'm going to switch, give a little bit and give you some insight on the importance of the semantics. Take this example, a simple question answering system. And in this particular case, you ask the question on a corpus, How many alcoholics are relapsing under the lockdown? I sometimes wonder how many, and then question is, does the person have addiction? And a deep learning model will say yes, and the true answer is yes. But now you take this example. Look at this example. And this example has negation. And for example, many episodes aren't characteristics of true depression. If you ask the question now, the question, does the person suffer from depression? The answer that sequence to sequence model will give would be yes. But the true answer is no. The reason is manic depression is a characteristic of anxiety and not depression. Deeper understanding of that is beyond the syntax, in this case involving mental health domain knowledge, is needed to be able to answer no. Okay, to be able to correctly answer. Other thing that you have learned very well, I hope, is this multi-chain, multi-hop reasoning. So you be able to reason that static electricity can cause sparks, and sparks can cause a forest fire. Hence, static electricity can cause a forest fire. But this is not something that can be done naturally by the deep learning system. So again, when you want to add this kind of additional processing of reasoning, you again need symbolic knowledge and hence knowledge graph. Now what is happening is that there have been some fantastic success stories of deep learning, especially examples are playing games, chess, or now AlphaGo, Go game. But what happens is that they may incorporate very, very simple form of knowledge of structure or the rule games, and that makes them more efficient. There is a very there's a kind of real major progress called AlphaGo in how can amino acids, a chain of amino acid, fold to give a protein folding structure. On here, this is a protein folding structure. Now in this case, deep learning can solve initial problem fairly well, but it does exploit knowledge from protein data bank, and then you can additionally improve this system if you want to support, and you'll have to use knowledge if you want to have the system support creation of structures that meet specific purpose or specific criteria, not all possible ones, or that so you want to ensure that they support specific functional properties. Then you'll need to infuse the knowledge in this process to get that. So that will be you can create a lot of structures, but most of them be meaningful. What you want is to give the scientist the structure that he is looking for to make a product or drug or whatever. In conversational AI, look at this example. Take your Alexa or Google Assistant or Siri, and you can ask, hey, whatever, how is your weather? How is the weather today? And say this weather. And can I play outside? Sure. But if you wanted to make it more personalized and contextualized, so for example, the person who's asking this has asthma. Now if you have asthma, then there is necessary, there'll be concept like pollen, ragweed pollen, which can cause phenotypes or asthma symptoms in a number of asthma patients. It is important to understand that there is in the environment there is ragweed, that there is a web service that gives you today's pollen level, and that if that pollen level is high, it is not good for asthma patient, or or it is not good for this specific asthma patient. So in that will be not the ragweed pollen and asthma symptom, these are contextualization, and then this patient is particularly susceptible to allergy from ragweed pollen is personalization. So if I want my chatbot to really support this kind of intelligent conversation, I will need to use knowledge graph. Here is an example of powerful example of knowledge graph. This is San Francisco Bay Area, and we took 1 year worth of data from the entire area. Two types of data: the sensors in the road network on 2000 and some individual road links, and Twitter data from from the this geographical area. And then we wanted to use traffic slowdown. We want to explain the traffic conditions and especially slowdown with the use of social media. So this shows example where traffic is very slow. The peak shows slow traffic. Number of taking longer time to pass something. And then we want to find in the same geospatial context tweets. So here at the location where there is slow traffic, this tweet was nearby, produced nearby, and it says location here. In yellow is the tagging or annotation, semantic annotation. So it tells you that there is a truck overturn, an injury, and that is what explains this slow thing. So now without knowledge graph, purely using deep learning, there is I can't see a way how you can use the textual Twitter data to explain sensory data here. It has to come that this intermediary of knowledge representation is very critical to be able to do that. And there's a lot more to this. There's a TIII paper, you can look at it. This is a pipeline for data, deep learning pipeline for NLP, and this shows some of the work that came from my group on each of those different topics. So, and many of them use deep learning techniques or enhanced deep learning techniques using knowledge graph, or yeah, the gluing, symbolic glue, gluing with symbolic, combining statistical AI and symbolic AI is system 1 and system 2. That is very, very hot now, very in demand now. And here I'm going to briefly show you how knowledge graphs and deep learning meet. So there are a lot of challenges with the deep learning here, especially when, for example, when the label is not binary, it is very difficult to ensure the consistency of labeling. And when you do labeling, there may be a lot of alternatives, slang terms and acronyms and all that kind of stuff, or supertype, subtype, that will be missing. All that can be given to you by their domain knowledge. So these are some of the reasons why you use deep learning. Let me move ahead and give you some insights into the process. So we kind of define the knowledge infusion methods into 3 types: shallow infusion, semi-deep infusion, and deep infusion. And generally speaking, what shallow infusion does is it uses embedding. So deep learning largely creates a vector out of data and or matrix, and we also create, in this case, create a vector or matrix out of data and combine the two to essentially get a little better result. Results may are marginally better. They may not be. It depends. Some problem can have a few percentage improvement, which may be significant though. In the semi-deep infusion, it explicitly impacts a layer and modifies the learning algorithm more deeply. And I'm going to show you an example. In the deep learning, deep infusion method, it does it at multiple level. So just like the neural network has multiple layers, we also in this case look for knowledge that is stratified, meaning has multiple layers or abstractions, and then infuse the knowledge at different layers of multiple layers of the deep learning layers. And so it's a very hard job, very difficult job, and the work is just still going on. There are a lot of examples in our survey paper of the sorts, but the what you infuse can be variety of things. It can be back of words, phrases from corpus, semantic lexicons, pronouns, verbs, nouns. So you can see all kinds of different things that people have combined or some with the deep learning algorithms. Here's an example where essentially what you do is retrofitting. So you are doing vector representation of words in tweets or embedding before retrofitting. So this is what it might look like. But you can see here damage, infrastructure affected. It's just kind of not clear what it means. But after retrofitting or use of such an ontology, you will probably get the representation that where infrastructure damage or damage to infrastructure or effect to population, these will be coming more closer, and you will say that these are in relation, these are to relationship, not population and infrastructure, right? In this example, this is EMR data and this is social media data. And what it shows is that you can do a clustering with deep learning, but what those clusters stand for or mean at an abstract level that humans can make sense of requires use of knowledge graph. So to say that these are all this cluster relates to suicide attempt and self-harm requires that you use a knowledge graph. This is an example from autonomous vehicle in which scene similarity detection is very important. For example, if I have school buses, and in US there is a law that you cannot drive faster than 25 miles per hour in a school zone. So you know that law will apply. You know that you need to reduce the speed. Whether you see the board that says speed limit or not, you must limit the speed. So if you can detect a similarity with the school bus, yellow school bus, then you can apply your knowledge, the rules that that are relevant to that. But to detect the similarity is extremely hard. And here in this paper shows, the use of knowledge graph here for autonomous vehicle is called scene knowledge graph, combined with knowledge, and using that to embed, in the sensor created data to understand variety of different stop cars or moving cars. These clusters are created with much better affinity and labeled using knowledge graph to be able to develop similarity. There are few semi-deep confusion algorithms. This is an example. So on Reddit, you see there are a whole bunch of Reddit, like this is bipolar disorder, and these are concept on the top. that come from DSM-5, which is the medical literature. This is the manual that people have to study if you are learning for if you're studying for mental health, if you're becoming clinician in mental health. So here it is uh, suicidal ideation concept, for example. These are the variety of concepts that come from the medical knowledge here. And the point is that you can see these colored bold terms. They come from the knowledge graph or knowledge base here. And understanding them is made possible because of the knowledge graph. Otherwise, it will be much harder to say what is relevant or with regards to mental health. Plus, a clinician would understand these texts with regards to similar knowledge that he has studied by reading and understanding DSM-5. If you tell him, oh, somehow through statistics I found this and this, they won't believe it. You have to explain to them in this term. So for that, for example, in this case, we took the text from Reddit and applied SNOMED to get treatment information, drug variety of other ontologies to get this other kind of information, DSM-5 for mental health conditions, society severity lexicon to understand these other things. So you can see that the doctors would see the whole thing in terms of treatment, observation, mental health. There's no way deep learning by itself do that. So this is a matrix that is created through analysis, and this matrix, this DSM-5 category and mental health related Reddits, and this matrix is a statistics that is combined with the your deep learning. So on the left hand side, green is your embedding model, word embedding model. On the right hand side is your DSM-5 DO is drug abuse ontology, and those incorporating those lexicon, you're creating this modified metrics to use as for much better results. So here this happens to be a text in bipolar subreddit, but it is not about bipolar. Instead, it is about this depressive disorder. And so we explain here why use of knowledge graph and combined with deep learning is necessary to be able to understand this kind of text correctly. Here's a powerful example where you start with basic technique, lexical and statistical feature. You get 30% error rate. You add some more features like TF-IDF, you get 27%. You add all of that, lot more features, you get 13%. Then you add DSM-5 knowledge hierarchy, you get to 4%. Big drop. Now it becomes hugely more useful. 3% when you add extra knowledge, and then some more knowledge, and you got to 2.5%. So it's a powerful example of how you can improve the results from deep learning by using knowledge graph. Similarly, we have example during epidemiology study and how the COVID spreads where it uses this. Now, the thing I explained to you, the thing that I talked about as a big impact on explainability and interpretability, which are very, very important for AI today. There is a big resistance in AI, and you need to make AI more trustworthy, be able to support causality, and so on and so forth. So these are some of the major challenges that explainability in AI can help solve. I will give you one last example. You can read this text here. Is this mental health related? The answer is yes. And so, using deep learning, but it asks which mental health condition is predicted. Answer, it says depression. That is false. And the true answer is obsessive compulsive disorder, OCD. How do you know that? How do you get to that? So here shows that DSM-5 and post-correlation matrix, in addition, support created from DSM-5 knowledge graph. When you use that, you get interpretable learning because you have all these bold terms, but you also get the correct answer that this is OCD from here. So this is a powerful example uh, and then this one shows you again the knowledge, graph explaining each of the words. Now this is the meaning of understanding, not the statistics that you cannot explain in a block box. Instead, here you are you understand variety of terms and phrases, what their meaning is, and what are the medical uh, context. So these are all medical representations that doctors and clinicians understand. Okay, is still one more example here. I'll pass that. Okay. Oh, okay. I think we are running out of time. Okay. So I hope I gave you enough insight today on why knowledge graph is very critical in advancing the machine understanding of content. And these are some of the related areas. Again, this is where knowledge-infused learning is making some impact, and where we are and how we go from iterative methods to much more powerful methods. Okay, let me end there.